Now, we can make things even more complex. We can ask the question what the probabilities are a week from today, given that today it is sunny. Well, we're not going to answer this right now, because what we're going to do is we're going to program this up in a minute. To do so, though, we need to introduce some notation. We're going to say that chi sub s super k is the probability that it's sunny k days from now. Similarly, chi sub ck, chi sub rk. Now, I could, of course, have said chi sub 0k, chi sub 1k, and chi sub 2k, but it's kind of convenient to use S, C, and R so that we know it's sunny, cloudy, or rainy. Okay, so here's our table again. And notice that we can ask the question, what is the probability of it being sunny on day k plus 1, given that the probability of it being sunny on day k is chi sub s super k. And the same thing for cloudy on day k and rainy on day k. Well, that's a matter of looking at what the probabilities are going from sunny to sunny, cloudy to sunny, and rainy to sunny. And you get this right here. And you can do the same thing to figure out what the probability is of it being cloudy on day k plus 1 or rainy on day k plus 1. And what you notice here is that this is a system of linear equations. That's a term that you may have heard before, and if not, I now introduce it. You also notice that this can be written as a matrix vector multiply, because this matrix vector multiply with this matrix is just this times that plus this times that plus this times that for the first one, and that must be equal to that, etc. Okay, so now we recognize matrix vector multiplication as a compact way of writing a system of linear equations. And then we can say, okay, well, we can call this matrix P, that's known as the transition matrix, and we can call the vector that tells us what the state is on day k, the state vector x super k. So we have a notion of a state vector, x super k, the state on day k, and a transition matrix P. So what we notice is that matrix vector multiplication is now used to compactly write a set of simultaneous linear equations. So here we have a vector that tells us the probabilities that today it is sunny, cloudy, or rainy. Well, we can look out the window and see what it is, and let's say that it is cloudy. As a matter of fact, I think today it is cloudy here. What vector represents that? Well, our good old friend, the unit basis vector, in this case the second unit basis vector. Okay, what happens if you ask the question, what are the probabilities of it being sunny, cloudy, or rainy on day 1, tomorrow, given that today it is cloudy? Well, that's a matter of doing this matrix times vector multiply, and if we plug in that today it is cloudy, then what we get is just this multiplication. But we could have simply said, oh, we know that when we do a matrix vector multiplication with a unit basis vector, we'd simply pick out the appropriate column. And there you have it. So we shouldn't be surprised. P, the transition matrix times a unit basis vector, picks out the appropriate column. If we now want to know what the probabilities will be for the day after tomorrow, all we need to do is take our transition matrix and multiply it times the vector that indicates the probabilities for tomorrow. We just calculated what that was, and when we multiply that out, we get the vector of probabilities for the day after tomorrow. And notice that this is a lot easier than writing out that tree that we would have had to write out otherwise. What now if we want to know what the probabilities are for a week from now, given that today it's sunny, cloudy, or rainy? Well, we know how to do that now. That's a matter of doing a bunch of matrix vector multiplies. But it's a lot easier if we use the computer to do the heavy lifting for us, and I'll see you in the next video.